Bismillahirrahmanirrahim. Assalamu alaikum and welcome to this session on NPE tools. So in this session we are going to talk about various ways of doing network performance evaluation, and we are going to focus on specific techniques that we have for experimentation on a system. So you may recall from our earlier lectures that we discussed that we can do experimentation on a real system to do network performance evaluation. We can also make use of analytical modeling. And finally, we talked of simulation as a way of doing network performance evaluation. But if we think of it, simulation is kind of like experimentation. But now we're not experimenting on the real system, but now we are experimenting on a computer model of the real system. So in this session, we'll be seeing the various diversity we have in experimenting and the various ways we can use experimentation for network performance evaluation. We can see that on one extreme, we can do real experimentation on real nodes in a production network. So this would require access to such a network, and it may be disruptive. On the other hand, we have the very abstract notion of simulation, in which we have abstract computer models representing everything. And then we'd be seeing in today's session, there is one further technique that we have, and we call that emulation, which is kind of a hybrid between a real experiment system or method and pure simulation method. So it is a kind of a hybrid in which we are making use of some real things. We're making use of implementation code. We're making use of some, let's say, application software that runs on hosts. But we are also making use of abstract models as simulations do. So we have both these things. And because of that, this hybrid model, we hope that it has the good properties of both simulation and experimentation. In this session, we're going to talk about these things in more detail. And we're going to talk about tools that we have for performing simulation and emulation. And also we are going to talk about the method of using test beds for experimentation. So this is kind of, this would be used for prototyping a research algorithm before it is actually deployed in a on a very large scale in a production network. You can have a smaller scale test bed. So these are the three things we're going to talk about today: simulation, emulation, and test beds. So let me give you an outline of today's session. Initially, in the first part of today's session, I'm going to talk about these three methods that I've just outlined. I'm going to talk about their advantages and their disadvantages. In the second part of today's lecture, we're going to talk about network performance evaluation simulation tools. We would see that many of these simulators have properties of being emulators as well. And we would see that these are very useful because they can allow us to iterate between simulation and test bed experimentation. And we would see that when we are actually doing network performance evaluation, it is an iterative process. Maybe you can start with a simulation analysis, and then when you have positive results, let's say, you would like to evaluate the performance of your algorithm or system in more detail or in more realistic settings where you are subjecting your system to actual workload. And then we can move away from the abstraction that we were using for simulation, and maybe we can make use of emulation, in which we are making use of implementation code, but we're also making use of abstract models. We'd be focusing on one simulator, and we'd be giving a very broad treatment of it. We would not be emphasizing the programming aspect of it. I'm just going to use the example of the NS3 simulator to show you a flavor of how simulators work. By no means this is a comprehensive treatment of this, and obviously we would need to learn this outside this class, but the idea is that using this introduction, you would at least know what simulators are and what is the normal workflow of a simulator. Finally, in the third part of this course, I'm going to talk about the method of using test beds for experimenting. And we'd be seeing that using such a method, we can get more realism. We have more realistic results because we are already incorporating aspects of the real world. But we'd be also seeing that creating test beds is not a trivial task. And therefore, it makes sense for us to build community test beds that all NPE researchers have access to. And we'd be talking about some efforts in this regard. So let us start with the first part of today's session, in which we're going to talk about NPE tools, and we are going to give a brief introduction. So the first approach that we have is the approach of simulation. So you can see on the slide, this should look familiar to you because we've done this before. We've seen the method of using simulation for performing network performance evaluation. And we said that the benefit of such an approach is that it gives you repeatability and it gives you the ability to reproduce your results, something that is very important for scientific analysis. And it also allows you to control your experiments. This is the benefit of simulations, but there is also a disadvantage, and that is a major disadvantage, that you have the issue of realism that is lurking, in the sense that in a simulation, everything is abstracted, everything is simplified. So in that sense, you're not performing network performance evaluation for the real workload, or you're not even implementing the real networking stack. So there is multiple levels of abstraction, and because of that, we miss the cross-layer interactions that work in real system, but they're not captured in a simulation. It is because, as you can see on the slide, we make use of models, both for modeling the input or the workload, and also for modeling the system. So you can see the input model and the logic model on the screen, and we see that both of them are typically abstract models. They are not real implementation code that is used in real systems. We don't have real traffic going on to our simulation. And because of that, we have this issue of realism, that the results that we have are only approximate, and they may not capture the reality of the world that we want it to capture. So if we want to introduce more realism, we can go to the other extreme of actually having experimentation on the real system. But we can also have a hybrid. And let's talk about that hybrid first. This thing is known as emulation. And this approach to network performance evaluation gives us improved realism with also the ability for repeatability or reproducibility, something that is difficult to do in actual experiments on the real system. So on the screen now, you can see that there are two ways of experimenting on a system. We can experiment on the real system. We can also experiment on a model of the system, and that is precisely what a simulation is. But then a simulation is, everything is abstracted there. What we can do is we can actually have some real code there. So that then defines a network emulator. So we can define a network emulator as a hybrid between a network simulator and a protocol implementation. And it provides, because we are making use of elements of the network simulator, it gives us a more controlled, reproducible environment for running live code. So if you're using emulator, we can actually we can make use of the protocol implementation that we have designed ourselves. And let's imagine that this thing is at the application layer. And we also want to make use of the real networking stacks. So we can have both of these, and we make use of a model in which all the nodes have the actual code running for our application software and for the networking stack. But then we are abstracting away certain elements of, let's say, the link layer or the physical layer, and we are simplifying that, and instead of the real system, we're making use of a model. this then defines an emulator. So if you see in this example, you have some real implementation code, and you also have some simulated aspects. So that is the reason we call an emulator as a hybrid between a network simulator and real implementation code. The benefit of this is that network emulation allows real end hosts and protocol implementations to interact with synthetic, simulated or abstracted elements such as network links, intermediate nodes, etc. So instead of a real network in between the nodes on which we have our code, we would have an emulated link, and we can define the characteristics of that ourselves. So we would maybe observe a real network and then capture it in a statistical sense and then relate that to the emulated network. But because this is being simulated, we have complete control of the conditions of the network, and we can change the conditions of the network at will, something that we cannot do on a real system. So this is the method of emulation. Let's proceed forward and talk of the life cycle of a network performance and evaluation project. So on the slide, you see that mostly we start with analytical models. And analytical models are limited in the sense that they can not model very complex systems. So there is only a few things that we can do with analytical modeling. We can make use of queuing theory, and we have results for that. But for realistic traffic, analytical modeling is almost impossible. We've seen that we have results only for Poisson arrivals in our session on queuing theory. And we've also seen that real traffic is not Poissonian in nature. So that creates a problem. And because of that, analytical modeling only provides us approximate results. So as a first step, it may be appropriate in certain cases, but it certainly will not give us exact results, something that we would expect to find in real networks. So the first stage then maybe would be analytical modeling, but then we want more realism. And for more realism, you can create arbitrary level of detail by creating a simulation model and then coding it in some computer programming language. So you see that on the slide that this produces a more realistic model. If you want more realism, you can make use of an emulation, and we can have an emulated network, but then we also have some real code. We have some real implementation. So this then becomes closer to the real implementation. And then after doing simulation, it has been observed that still we do not have very accurate results. And before we actually deploy our system or our algorithm at a very large scale, typically it is advisable that we do a testbed experimentation of this system. And this is the trend network performance evaluation is taking. Many people have now lost their belief in simulations as the final tool that we must use. And in most current research journals, only simulation papers are not treated with a lot of respect, because they say that, okay, you have done simulations, but the performance of your system on real networks is not clear because your simulation may be too abstract. And because of that, a clear trend is towards adoption of test-bed methods of doing network performance evaluation. But the key idea here is that this life cycle is not a one-way cycle, that you must go from an analytical model to a simulation to a test bed, but it is in most cases a to and fro cycle, that you go first of all, let's say you do simulation, and then you do test bed implementation, and based on measurements on that system, you may think of a better design, and you may think that this is not the way I want to implement my system when it goes for deployment. And because of that, you may go back, change your model, and then because it is typically easier to do simulations, you may want to do simulations before you do test bed experimentations. So because of this iterative nature, the important thing is that we do not have tools that work in isolation. Ideally, we want the effort that we've done in simulation to also count when we actually do a testbed experimentation. We would like to use the same code, if possible, on a testbed. And luckily, research has actually focused on this question, and now we have more interoperability between simulators, emulators, and testbeds. This is something that we would do later on in this lecture itself. So the key idea then is that network performance evaluation is an iterative process. It requires much to and fro looping between analysis, simulation, and emulation, and testbed implementation before actual deployment can take place at scale with real users. So now I can summarize the discussion of this part of today's lecture by talking of the three methods of experimental network performance evaluation. These are the methods of simulation, emulation, and testbeds, where simulation makes use of abstracted models, emulation makes use of abstract models, but with also actual implementation. It's a hybrid between abstract models and actual implementation. And in testbeds, we have actual implementation, but on a limited scale. And after that, you can deploy your system or algorithm at large scale. So let us see firstly, what are the advantages and disadvantages of simulation? So simulation actually makes use of abstracted models. And because it does not have any implementation aspect, it is not going to be as costly as, let's say, experimentation on a real test bed. So let's first of all list down the advantages of simulation. Simulation is insightful because we can closely control the settings in which we are running our simulation. We can make use of this and then come to scientific conclusions on the basis of our results. So it is insightful, it is repeatable, and these two are the main benefits of using simulation. It is scalable and fast if we compare it to other methods of experimentation, namely emulation and testbed. Emulation is also like simulation, but when we come to testbeds, experimentation on a testbed typically takes more time. Also, simulation is cheaper than conducting an experiment on a real testbed. We also don't need any deployment as such because we're making use of abstract things, of only models that are programmed in computers. We don't need to deploy a real network. So these were the benefits of simulation. The disadvantages are the lack of realism. Because this is model-based, our results are not going to be very realistic because they are working on simplified models of reality, and therefore the answers are only going to be approximate. When we talk of emulation, emulation has many of the benefits that we talked about in simulation. Emulation also is insightful. It also has repeatability. It is also scalable and fast like simulations. It is also flexible and cheap like simulations. The main advantage it has over simulations is in its improved realism because it's making use of real implementation code. But then it is also model-based. Aspects of networks are still modeled or emulated, and in that sense, we're not going to have a completely realistic representation of reality. If we want to have a completely accurate and realistic depiction of the real system, we have to work on the real system. So a way of doing that is the way of doing experimentation on a test bed. But then you only have, limited advantages. Obviously, this advantage is a big advantage that you have a lot of realism, but then you have many significant disadvantages. The disadvantages are that this testbed is like a black box. So you don't gain a lot of insight by doing testbed experimentation because you have lesser control over the network conditions. And because of this lesser control, your experiments are non-repeatable. Because if we have a real testbed, many aspects of the actual network are outside your control. And because of that, you cannot recreate the exact situation again and again, which is of a great benefit when we're doing scientific analysis. Also, it is not a scalable solution to create private test beds. Even if you're creating a public test bed, because these are real nodes, they will be costing money. And therefore, you cannot scale a test bed to, let's say, thousands and thousands of nodes. And because of that, it is not very scalable. It is slow as well, because experimenting on the real system takes time. And because of that, it is also not very flexible. Finally, when we are creating a test bed, we need experienced people who can manage the test bed. And they are going to be a permanent feature of test bed operations. So they would be in a maintenance team that are managing the operations of the network and also are maintaining the network. So this then presents a clear summary of the three approaches that we've studied for performing experimentation. The main insight of this part of today's lecture is that we cannot just work with one experimental method outlined on this slide. We need all three methods because they give us distinct advantages and they also have some disadvantages. So because of this, we make use of the NPE life cycle, which I showed you just a little while ago, in which you are looping between the various experimental methods according to your particular needs. So that's the main idea I want to give from this session. Let's now talk of the next section, in which we are going to talk about network performance evaluation simulation tools, and we'll be covering the NS3 simulator, which also has the ability of doing emulation. So then this becomes a simulator/emulator tool. So before we even talk of NS3, let's now think about the various ways we can make use of simulations. So as outlined in a previous lecture, we saw that there are many ways of creating simulations. You can have what is known as a home-brewn simulation. You don't make use of any package. You don't make use of any simulation language. You create everything yourself. But then the problem with such an approach is that it is very hard to get such a system right. And it is very wise that we use the contributions of other people rather than reinventing the wheel. So the first category shown on the slide, the category of using general purpose programming languages, may be appropriate for a small task, but if you are considering making a large simulation, then it is often wise to make use of either a simulation language or a simulation package that is customized for the particular domain that you're working in. So for people working in operations research, they have specialized packages. For people working in logistics or in some other domains, they would have simulation packages that are optimized for their domain. People working in the aerospace industry will have their own simulator and will have their own simulation packages that have routines written which are necessary for that domain. So since we're talking of network performance evaluation, we're interested in network simulators. And there are many such network simulators. Some of them are commercial, while others are completely free. The commercial simulators have many good features. An example of a commercial simulator is the OpNet simulator, which is GUI-driven simulator, in which you have a lot of flexibility and you have a lot of models already there in the library for you to use. We also have, luckily, free and open source network simulators available. And we're going to talk about one of these just a little later when we talk of NS3. But there are other free network simulators as well. For example, you have the OmNet++ simulator, which is based more or less on the OpNet simulator, but it is a free version of it. It is also graphically driven, so it is easy for newcomers to understand and adjust to this package. So the idea then is that if you are working on a new simulation, most of the times you'd be making use of a simulation package for your domain, and for our purpose of network performance evaluation, we'd be making use of network simulators. So let's focus on one of these simulators. We're going to talk of the NS3 simulator as a representative example of the broad class of network simulators. So the NS3 simulator is actually not completely new simulator. It has a precedent. It is sourced mainly from the NS2 simulator. And the NS2 simulator is a very popular simulator, and it has been used for a lot of research. Unfortunately, there has been some credibility crisis in the NS2 simulator. Lately, many people have questioned that the NS2 simulator has many models that are not validated. And also because for some time the NS2 simulator was not managed by dedicated staff, the entire code base became unmanageable, and now it is very difficult to get various models of NS2 working together. And because of that, we have this new simulator which is based on NS2 but only very loosely. It is not backward compatible completely with NS2, and we'd see for what reasons very shortly. But let me now outline the history or the chronology of events that led to the creation of NS3. So on the slide now you can see a timeline, and we see that the first simulator which really had an impact, I'm talking of network packages or network simulators, is the Real simulator. The name of the simulator is Real, and it was created by Keshav. And this was the basis of the first network simulator, the NS simulator. The NS simulator was proposed in 1990s, and then in the late portion of 1990s, around 1996, NS2 formally came into being as the next version of NS1. And there was a major period in which NS2 was being developed. And this project of development of the NS2 simulator was funded at various times through various agencies. So you see that from 1997 to 2000, it was funded by the DARPA agency. This agency is the Defense Research Agency in the United States of America. And then after this project finished, again NS2 was funded by projects belonging to DARPA again and to the National Science Foundation of the US. So because of that, you had funding and people were working on improving the quality of NS2 simulator. And people were proposing models, and these contributed models were being integrated into the main simulator. And by 2002, 2003, NS2 had become a very large simulator, and most of the models were already present. So you only had to configure the model, but the core model was already present. And many of the tasks that we have to do for network simulation were already built into the NS2 simulator. The only aspect was that there was no clear validation process, and because of that, many bogus models came into the real code base. And because of that, people lost credibility in NS2 simulations in particular, and in the process of single-handedly depending on simulations for network performance evaluation in general. And because of that, the trend of using test beds and emulators developed. But then simulation also has its place. As described in the earlier part of today's lecture, simulation has many benefits as well. So if we have realistic models, they may be abstract models, but they are good representation of reality, then we can make good use of simulators. And that was the purpose NS3 was proposed. And this project started in 2006, and it made use of certain existing network simulators. So you see at the bottom of the slide that this used the YANS simulator, the Georgia Tech Network Simulator, a major portion of NS2, and it tried to incorporate what could be easily incorporated, but then it also worked on creating a new base in which you have many desirable features. We want our network simulator to be scalable because we want to create simulations of thousands of nodes. So we want a simulator that can scale to very large networks. And we also want our network simulator to have the ability to extend to a testbed implementation. As mentioned in the earlier part of today's lecture, we have this looping to and fro exchange between simulation, emulation, and test beds. So this was recognized in the design phase of NS3, and it was an explicit goal that we wanted NS3 to have features of support for all these three kinds of experimental methods. We want support not only for simulation, but also for emulation, and also for extension to a testbed implementation. We don't want to rewrite our code every time. We want that all the work that we've done for the NS2 simulator, it should be extended and it should be used. We may write some more code, but it should not be the case that whatever we've done for the simulator part of our analysis, we don't want it to go to waste. So this is, in brief, the background of the NS3 simulator. The NS3 simulator, for those who know the NS2 simulator, is significantly different. I will highlight now how it is different. In that sense, we can say that NS3 is only a spiritual descendant of NS2. It is not exactly like NS2, nor does it try to be like NS2, because NS2 had some problems as well. And because of that, we want to improve the system, and a decision was made that while we will try to incorporate as many models as we can, but we will not try to be exactly backward compatible, because that can create issues. So as seen on the slide, you can see that in NS2, we had a system in which the core of the simulator was written in C++, but you also had a complementary language of TCL. You had the OTCL and the TCL-CL, that is TCL with classes and object-oriented TCL, to complement it. And because of it, learning NS2 was difficult. It was a steep learning curve because many students did not have exposure to TCL and they had to learn this language. So a decision was made for NS3 that we will not make use of TCL. Instead, in line with the current trends, we'd be, first of all, in a sense, we would be creating a new core of the simulator. It would still be in C++, but now we'd be explicitly coding our core according to some design guidelines. We'd be aiming for high scalability, and we would be aiming for support for both simulation, emulation, and testbed implementations. So on the slide, you can see some similarities to NS2. You see that NS3 also has an object-oriented software core in which it uses the C++ language. It also tries to incorporate the models of existing simulators, and many NS2 models have been incorporated. The major differences are that we are not using TCL anymore, and instead of it, for writing scripts, we're making use of Python. And then most of the core is rewritten according to modern software engineering practices, such as using smart pointers, templates, callbacks, so that we have a more stable system. The slide that you can see on the screen now actually summarizes the main features of NS3. So we've seen that there is an explicit design consideration of testbed integration, and we want to support emulation, because using emulation we have increased realism along with repeatability. And then there is increased focus on software integration, and we are going to create a new software core that has many new features focused on scalability. The attention on realism is very focused, and because of that we have the focus on both emulation and testbed, and we also have support for virtualization. There are some other important features as well. For example, the attribute system allows us to access attributes of objects without a lot of effort, and we can adjust them without requiring a recompilation. So this is a good feature of NS3, and it allows us fine-grained control of accessing and setting the various attributes of different objects. Many of the animation tools that we have for NS2 are being worked over to have NS3 versions, and we are creating new versions of animation tools. So this is something that is important, because in network simulation we also want to have the ability of animating the run of our simulation. Lastly, a very important aspect of NS3 is its tracing architecture. And because of that, we have a concept of trace sources and trace sinks. And we can define trace sources to send their trace data to the trace sinks, which are then specialized nodes that are going to function for analyzing these traces. And the good thing about NS3 is that it allows us to print traces in many formats. It also allows us to print a trace file in the PCAP format, which can then be analyzed using common softwares like Wireshark and other similar software that can work with PCAP file format. So let us now talk about some very basic models and base classes of NS3 so that we get a flavor of NS3. Certainly it's not the point that I don't want to emphasize the programming part of NS3, because we can do very little in a single lecture. The idea is that I just show you the broad structure of NS3 so that you get an idea, and then you can work on your own, and through tutorials that are available on the NS3 site itself, you can actually learn this language. So the base classes that NS3 uses are defined on the slide. You have around 5 to 6 very important classes. The first fundamental class is the node class, and then you have net devices, then you have channels, protocols, applications, and packets. These are all abstractions. So we can make use of these abstractions to define the real system that we are trying to model and simulate. We can see the flow of a typical simulation on the slide now. You see that there are many things a typical network simulator has to do. Firstly, we need to define the topology, and then we make use of multiple models. We've seen some models here, and then we are going to study some more. As an example of models, we have the Wi-Fi model, and there is a fairly accurate model of Wi-Fi in NS3. We also have something known as NSC, Network Simulation Cradle, in which we are making use of actual real-world stacks in the simulator. So we make use of the Linux TCP/IP stack, and we make use of that TCP portion of that, and we run it on top of our simulator. We can also incorporate the version of BSD stack, and then we incorporate it in our networking simulator. So this is the concept of NSC. Along with models, we also need to configure the models. So just defining the models is not enough. We need to give it attributes which defines the realistic network that we are trying to model. And thereafter we have to execute the simulation. And all this while we make use of random variables. So I would like you to tie this with the things that we've studied earlier about simulations. And this NS3 is just a simulator. So everything that we've done earlier applies here. We need to define a topology. We need to configure our models, and we need to execute our simulation. And typically a single execution or a single run is not going to tell us a lot. So we need to perform multiple runs and then perform output analysis of it. According to sound statistical techniques, if you recall, we have done this at length in our dedicated session on output analysis. The important feature that NS3 offers in this regard is that it can allow us to export trace files in the PCAP format, and therefore we can analyze it using typical packet capture software like Wireshark and other similar software. We also have various visualization tools available, and we can make use of that to analyze the output of our simulation. So let me come to an example through which I want to clarify the working of NS3, and this is going to be a very broad description of it. In this example, we are going to create a simulation of two nodes connected by a point-to-point link having IP addresses 10.1.1.1 and 10.1.1.2/24, and these two nodes will be used to exchange a single UDP packet from UDP client on one machine to UDP server application on the other machine. And by the way, this application is borrowed from the NS3 code. If you actually implement NS3, there would be an examples folder, and this is the first example there, and this would have the name first.cc. And we're going to inspect this file and see how the simulation is taking place. So right at the top of the code, you would see that you would have a few include statements, and these are necessary because we are making use of multiple classes and objects later on, and we need to give declarations of that. So this is standard C++ practice that you have these include lines, and then you see that you have the main function, and this is again like you have in a typical C++ program. And because of that, we stress that NS3 simulation is just a C++ program, so there's nothing special here. Inside this main program, we'd be calling other objects, and they'd be setting up our topology, and then we'd be scheduling that and running the simulation. So starting first, we would be making use of topology helper objects. These are objects defined by NS3 developers to make things easier for users of NS3. So NS3 has many low-level objects, and it also has these helper objects that we can call, and these helper objects will in turn call these low-level objects to do whatever we specify. So we're going to work on a higher abstraction level. So if you see the main file, the first two lines are going to enable the logging capability of the UDP eco client and the UDP eco server that we're going to exchange packets between. And then you see the container statement. This is one of the features of NS3, that we make use of helper API and container objects. So instead of specifying and working on every node and then on every network device and then on every channel, we put all of the nodes in a node container, and then we apply a common operation to all of the nodes inside the node container. So in fact, we're going to make use of the hidden or embedded for loops in the helper objects to make things easier for us. So here we are firstly defining nodes as an object of type node container, and then using a method of this object, we are going to create two nodes. So these are the two nodes that we have shown on the bottom of the slide, and both these nodes are part of node container. Now that we've defined node, we also need to define the link which are going to connect these two nodes. And because this is a point-to-point link, we make use of the point-to-point helper object, and we define a new object titled point-to-point, and then using its method, we set the attributes of that link. For example, we set the data rate to 5 megabits per second. We set the channel attribute, the delay of that, to 2 milliseconds. And then we are going to create devices and put them in a net device container. Just like we did for nodes, we're going to put all the devices in the net device container and then apply the install function of point-to-point on them. So the nodes are given as attributes of that method, and what we have then is devices. So that is an object of type net device container. Again, in a similar fashion, we would be making use of these topology helpers to create further levels of abstraction. For example, up till now, we have created nodes and we have created network devices, but we also need to give IP addresses. And the way of doing that is shown. You should note that in a similar fashion, we are making use of the container object, and then we are applying a function of the topology helper. At this step, we have configured the node, the device container, and the IP address. Further on, we can now talk about the application, because at the end, we need a UDP client application and we need a UDP server application. And then we need to schedule events. So if you see on this slide, we have the eco server helper, and we are defining an object eco server, giving it an attribute of 9, that it is going to listen on port 9. Also, we are scheduling this server to start at 1 second and to finish at 10 seconds. For the client, if you observe, you need to set more attributes. And we are defining those attributes here, and we are also scheduling the start and stop of this client. So having defined all of this, we've defined the node, the net device, we've defined the link, and then the IPv4 stack, and finally the application. We can actually exchange the data by running the simulator. So NS3 has a simulator class. We call the run method, which will run the scheduled events. And so you can see the output on the slide. Once the simulator completes, everything has to be cleaned up, and that is done by the destroy method. And finally, the simulation ends. So this gives you a very broad introduction to NS3. For more details, you should consult the main NS3 site, and the appropriate link is given on the slide. Let's now talk about the third part of today's session, about NPE testbeds, in which I'm going to give you a very brief introduction to testbeds and the various testbeds that we have. So a quote which is relevant here is given on the slide. You see that this is coming from Nick McKeon, Stanford professor, who says that for years the community had to rely on simulators, which now seem a little dated. And it's not clear who was convinced to adopt anything new based on NS2 simulations. So this is the same lack of credibility that I've already talked about earlier. So because of that, simulations alone are not enough. We need more realism, and for that we need to do testbed experimentation. But creating a new testbed is not trivial. It costs a lot of money, and it is difficult to manage. And because of that, luckily we have some public testbeds that are available to all NPE researchers. So the first one which I'm going to talk about is the Planet Lab testbed, which is a research and deployment platform. We've already talked about this in our earlier session on internet measurement. You see that on the slide, this is a very large testbed. This has proportions of our planet, and that is why it is kind of a virtual lab that is of planetary proportion. This actually spans the entire planet. It is like the internet, but we would be seeing that it is an overlay network. It uses the internet to connect Planet Lab nodes, and because of that, it is known as an overlay testbed. And this is important in the sense that it allows us to introduce disruptive innovations in our overlay network without requiring any fundamental change in the physical substrate. In the actual networks, the actual internet does not have to change, but only our overlay nodes are changed, and we can test our applications. The good thing about Planet Lab is that it is very diverse. It has now more than 500 sites and more than 1,000 machines. And it supports a paradigm of distributed virtualization. The idea would be clarified, but very briefly speaking, the idea is that everyone who is interested joins this Planet Lab consortium, and the person or the organization does it by dedicating a device and connecting it to the Planet Lab testbed. And then this machine is going to run custom software, which is provided by Planet Lab. Typically, it is a Linux-based system running some specific software created by Planet Lab people to enable this distributed virtualization. And using this distributed virtualization, they can give slices of the entire testbed to people who are interested. And because of that, people can work on a global testbed. So they can actually see before they deploy their application on the internet that what is the performance going to be on a real network of the proportions of internet. So this concept of distributed virtualization is very important, and this is a very hot topic. In this, a user reserves resources on multiple nodes at once, and these resources are known as a slice, and these are interconnected through a network overlay. Let me show you what a network overlay is. You can see on the slide, on the base layer, you have a physical network, and then some of the nodes of this base network are connected in what is an overlay network. Overlay network seems to be a new idea, but even the initial internet was an overlay network on top of the telephone network, in which you were using the telephone network for base connectivity. So when we talk of an overlay network, physically they don't have direct links, but logically speaking, through software, we have this notion of an overlay network in which the nodes think that they are just using the physical networks for transport, but they have direct pairing with other neighbors. So this is a very interesting concept, and it provides an opportunity to introduce disruptive technologies, because now the entire internet, it's not necessary to change the entire internet to support your application. You only need to do it inside your slice. You don't even need to change all the Planet Lab nodes because you have distributed virtualization. You are given kind of a dedicated internet of your own, and in that slice you can do anything that you want. So this virtualization thing is very important. It can be seen on the slide now that you have slices on substrate physical networks. So you have physical network, even the overlay network, it is then virtualized, and multiple researchers are given different portions of your Planet Lab testbed. And then these slices are embedded in a substrate of networking resources, which is virtualizable and has programmable components. So you would see that these are very important trends, the trends of virtualization and of programmability. So this is something that we learn from Planet Lab. You see that in the first instance, lines between the red slices define a single slice. But then the same network may be used by some other researcher. And you see that in the lines connecting the blue slices. And that is the slice of the Planet Lab testbed given to one other particular researcher. So this is a very important concept. Another testbed that we can learn from is the MULab testbed that you can see on the slide. This is different from the Planet Lab testbed in that the Planet Lab testbed had global proportions. You had devices, physical devices deployed at various places across the globe, and they were connected in an overlay setup. In an MULab, you have a kind of an internet emulated in a single room environment. You have a lot of hardware and many cables connecting these devices, and then through pure software you are emulating whatever network that you specify. So the idea here is that an emulated experiment allows you to specify an arbitrary network topology, giving you a controllable, predictable and repeatable environment, including PC nodes on which you have full root access, running an OS of your choice. So in this aspect, it is like the Planet Lab nodes, in which you also have full access and you can install from a list of operating systems supported, any operating system of your choice. And then you are a root user there. So that is very important. Because of that, you can implement any application that you want. So let us see how EmuLab works. EmuLab was created by University of Utah, and they created a software that can manage all this hardware and create arbitrary topologies. And also, this is a public facility open to researchers worldwide. So you can ask for an account and then do experimentation on this EmuLab remotely. So EmuLab is both the software that they've written and also this hardware facility. But using the software that they've written, many people have created their own EmuLabs. So creating your own EmuLab requires you to also have all the equipment. But if you do not have that much money, you can actually join the University of Utah's EmuLab and ask for access. So let's see how this works. On the screen now, you can see how topology is specified through a graphical user interface, and then you can specify using a variant of the NS2 language. In that syntax, you can define your topology and your events, and then you can create an experiment using the EmuLab interface, and then that is transformed to physical nodes through particular techniques developed in the EmuLab software. And the network aspect of the network that you've specified is emulated, and the nodes that you've specified, you have full access to it. So this is a very useful facility, and it complements very nicely the facility offered by Planet Lab. So with this, I come to the end of this lecture. Let me conclude this lecture by giving a few remarks. The first remark I'd like to give is that many simulation tools exist, both free and commercial, and they should be explored instead of just relying in general purpose programming languages, because we should avoid reinventing the wheel and exploit the work that is already done. We should note that simulations suffer from the problem of realism because they make use of abstracted models, and we can make use of emulation because that is an attractive alternative, because it provides repeatability and improved realism at the same time. And lastly, we noted that testbeds offer an opportunity to perform network performance evaluation on real systems running real code, but they also had some disadvantages. With this, I come to the end of this lecture. Thank you for joining. Assalamu alaikum wa rahmatullah.